Hey y'all. So fortunately I'm not feeling well, so making these video notes going over the quantitative graphing notes and the translating between graphs worksheet that we're going to do today. Let me just. All right. So for the first one, so the area of velocity and acceleration graphs, this was the second thing on y'all's handout. It had a bunch of graphs put together. So we have a bunch of velocity graphs and we need to find the displacement. And we want to find them two different ways. So we have the formula average velocity is displacement times time. That means we can multiply both sides by time and get the displacement or change in position is average velocity times time. And we can also find the area of the shape formed by the line. So here we have a velocity of -4 meters per second for a time of 5 seconds. If we use the average velocity formula, delta x equals v average times delta t, that's -4 meters per second times 5 seconds, that's -20 meters. And if we take this and draw a line up to the time axis to v equals 0, we've enclosed a rectangle. And the area of that rectangle would be 5 seconds, the base, times its height, negative, because it's below the axis, we have to call that negative height, meters per -4 meters per second, which also gives us -20 meters. All right, let's look at this one. We have a velocity of 10 meters per second for 5 seconds. So if we do 10 meters per second times 5 seconds, that's a displacement of 50 meters. And if we draw a line down here to the time axis, we have a rectangle with a base of 5 and a height of 10. So that's an area of 50 meters. Now, if this one where the object changes velocity, it moves at 2 meters per second for 2 seconds, and then at 6 meters per second for 3 seconds. We just find the displacement for each segment and add them up. So we'd have 2 seconds as the base of this rectangle times 2 meters per second. That's 4 meters or 4 meters. And for this one, we have the base of 3 seconds times the height of 6 meters per second. That's 18 meters for a total displacement of 22 meters. And then right here, we have an object moves forward at 3 meters per second for 2 seconds. Then it moves backwards at backwards at 4 meters per second. So a velocity of -4 meters per second for 3 seconds. So that's a negative, first a positive displacement, then a negative displacement. The area of this rectangle right here, we have 2 times 3, that's 6. The area of this rectangle here, we have 5 times -4, or 3, because that's 5 or 2 to 5. So that's 3 times -4 is -12. That's 6 meters. So we have it moves 6 meters forward, 12 meters backward, so a total displacement of -6 meters. One thing to keep in mind, though, with the if you're asked what the distance this object traveled is, it travels 6 meters back or forwards, then 12 meters backwards. That's a total distance traveled of 18 meters. All right, so all of these were constant velocity problems, but this also works if you have constant acceleration. So here the velocities may be changing, but, and this is real important, for constant acceleration only, you can find the average velocity with the average of the initial and final velocities. So here we have a velocity increasing from 0 to 5 meters per second over 5 seconds. If we draw a line down, we get a triangle. The area of that triangle is 1/2 base times height, 1/2 5 seconds times 5 meters per second. That's 12.5 meters. And the average velocity, well, its initial velocity is 0 and its final velocity is 5. So the average velocity is 2.5 meters per second. And that times 5 seconds also gives us 12.5 meters. Here we have the object starting at rest, and it moves backwards at accelerating to -10 meters per second after 5 seconds. So the area of this would be the triangle, 1/2 the base, 5 seconds, times the height, -10 meters per second. That's -25 meters. And if we look at what the average velocity is from 0 to -10, the average velocity is -5. That times the time also gives us, it's a typo, should be -25. Izzy, stop eating the flag. All right, what about this right here? So the object's moving forward the entire time. The velocity is never negative, but it's slowing down. It starts at 10 meters per second, but then after 5 seconds, it's only moving forward at 5 meters per second. So the average velocity there would just be 7.5 meters per second times 5 seconds gives us 37.5 meters, which we could also, that's basically just the equation for the area of a trapezoid. We did 1/2 base 1 plus base 2. Remember, when it comes to a trapezoid, it doesn't matter what orientation it is, the bases are the parallel sides. So that's 1/2 of 10 plus 5, then times the height, which is the perpendicular distance to that base 5, gives us 37.5. Or you could also do the area of a rectangle with a height of 5 and a base of 5, plus the area of a triangle with a height of 5 and a base of 5, and get the same result. All right, this object, it moves at, it starts off moving backwards at 2 meters per second, and it speeds up. After 5 seconds, it's moving backwards at 7 meters per second. So the average velocity is -4.5 meters per second. And then that times the 5 seconds gives us -22.5 meters. We could also find its displacement with the area of this trapezoid. 1/2 base 1 is -2, base 2 is -7, times the height, the perpendicular one to the bases, 5, gives us -22.5. All right, this one, our object changes direction. We have a constant acceleration, but it changes direction as it's moving. It starts off moving backwards at 2 meters per second squared, but over 2 seconds it slows to a stop. Then it starts speeding up in the forwards direction, and from after 5 seconds, it's moving forwards at 3 meters per second. So the average velocity of this would be, well, -2 plus 3 divided by 2, that's 0.5 meters per second, times the time, 5 seconds, that's 2.5 meters, or the area. So this triangle, it has a base of 2 and a height of -2, so that's -2. And this triangle, it has a base of 3 and a height of 3, so that's 4.5. So that adds up to 2.5, same as before. But again, one thing to be wary of, if you were asked to find the distance traveled in a scenario like this, you'd have to add up the absolute values of these. +2 plus +4.5 to get 6.5. All right, finally, what about acceleration? Well, acceleration is the rate of change of velocity, or the slope of a velocity graph, which means we can say that the average acceleration of something would be delta v over delta t. Just like velocity is the slope of a position graph, and it's also equal to delta x over delta t. Acceleration, we know, is the slope of a velocity graph, so it's equal to delta v over delta t. Well, just like by looking at slopes, the slope of position gave us velocity, and the slope of velocity gave us acceleration. The area under velocity gives us the change in position, and the area under acceleration can give us the change in velocity. Here we have an object accelerating at 2 meters per second squared for 5 seconds. So change in velocity is average acceleration times time. That's 2 meters per second squared times 5 seconds, or 10 meters per second. And if we draw a line down to the time axis, we've enclosed a rectangle, and the area of that rectangle is also 10. Here we have an object accelerating at negative 5 meters per second squared for 5 seconds. So if we draw a line up to the time axis, we've enclosed a rectangle. In the area of that rectangle, we have a base of 5, a height of negative 5. So the change in velocity is negative 25 meters per second. And here we have an object that first it accelerates at 3 meters per second squared for 2 seconds. Then its acceleration decreases and it only accelerates at 1 meter per second squared for 3 seconds. The change in velocity is just the area of these two rectangles made by drawing a line down to the time axis. So this rectangle has an area of 6, and this rectangle has an area of 3. So the total area and the total change in velocity is 9 meters per second. All right, excuse me. All right, let's look at the other worksheet then. So, again, to wrap up what we've seen so far, the slope of a position time graph is the velocity, and the slope of a velocity time graph is the acceleration. The area under an acceleration time graph is the change in velocity, or delta v, and the area under a velocity time graph is the change in position, or delta x. That's what we just learned, those two things. So here we've got a position versus time graph. The object goes from 0 to 5 meters after 5 seconds. Then it holds position for 5 seconds. Then it moves forward 10 meters in 5 seconds. Then it holds position for 5 seconds. Then it moves backwards 15 meters in 10 seconds. So how far does it travel during the first 5 seconds? 5 meters. During the second 5 seconds, 0 meters. During the third 5 seconds, 10 meters. From 15 to 20 seconds, 0 meters. And from 20 to 30 seconds. So how far implies it's looking for a distance, and it's a distance of 15 meters, or a displacement, since it's further back from where it started, moved in the negative direction of negative 15 meters. It's standing still from 5 to 10 and 15 to 20 seconds. That's where the position graph is constant, so constant position. And these are all linear segments, nothing curved, so it never accelerates. And then to draw a velocity time graph, well, let's look at the slope. So slope from that segment is 1, slope for that segment is 0, slope for that segment is 2, slope for that segment is 0, slope for that segment is negative 1.5. So our velocity time graph would look something like this. First, it's a constant velocity of 1 meter per second for 5 seconds, then 0 meters per second for 5 seconds, then 2 meters per second for 5 seconds, then 0 meters per second for 5 seconds, then negative 1.5 meters per second for 10 seconds. All right, let's take a look at this velocity time graph. So this is So we have some linear segments, which means we have acceleration. Yeah. During which intervals is the object accelerating? So anywhere the velocity isn't constant or horizontal. So during segment A, during B, during C, during E, and during F. When is the speed increasing? Well, that's when the velocity is getting further from zero. So that's from 7 to 9 seconds and from 25 to 30 seconds, or along C and along F. And when is it slowing down? Well, that's when the velocity is approaching zero. So that's from 0 to 5 seconds, 5 to 7 seconds, and 15 to 25 seconds, or A, B, and E. When is the acceleration the greatest? Acceleration is the slope of the velocity graph, so the acceleration is the steepest along B and C. When is it standing still? Well, it's at rest, at least instantaneously, when the velocity is zero, when it crosses the axis at 7 seconds and 25 seconds. All right, and now we need to calculate displacement. What's the displacement during A? Well, if I draw a line up to the time axis, I've enclosed a trapezoid with a height with one base of -10, the other base of -5, and a height of 5. So that's 1/2 times -10 plus -5 times 5, which gives us -37.5. During interval B, we have a triangle with a base of 2, a height of -5. So 1/2 times 2 times -5 is -5 meters. During C, we have a triangle with a base of 2, a height of 5, positive 5. So 1/2 times 2 seconds times 5 meters per second, that's 5 meters. During D, it goes from 9 to 15 seconds. The velocity is 5 meters per second. So the rectangle, the area under this segment is 6 times 5, or 30. During E, if we draw a line down here, we've enclosed a triangle. It has a base of 10 and a height of 5. So 1/2 times 10 times 5 is 25 meters. And then during F, so this is a triangle with a height of -5 and a base of 5. So that's 1/2 times 5 times -5, or -12.5. All right, we're asked to find the total displacement. So for that, well, just add up the displacement along each time interval. -37.5 meters minus 5 meters plus 5 meters plus 30 meters plus 25 meters minus 12.5 meters gives us 5 meters. And to find the total distance traveled, that's the absolute value of -37.5 plus the absolute value of -5 plus the absolute value of 5, since it's covering more ground even when it's moving backwards, plus the absolute value of 30, plus the absolute value of 25, plus the absolute value of -12.5, which is 115 meters. So the object only finishes 5 meters ahead of where it started, but it moves a total distance of 115 meters. All right, we're asked to make an acceleration time graph for the above scenario. Acceleration is the slope of the velocity graph. So from 0 to 5, the slope is 1 meter per second squared. From 5 to 9, let's see, that's up 10 over 4. That's positive 2.5 meters per second squared. From 9 to 15, that's constant, so the slope is 0 meters per second squared. From 15 to 25, we go down 5 over 10. That's negative 0.5 meters per second squared. And from 25 to 30, we go down 5 over 5. That's negative 1 meter per second squared. So from 0 to 5 seconds, we have an acceleration of 1 meter per second squared. From 5 to 9 seconds, an acceleration of 2.5 meters per second squared. From 9 to 15, 0. From 15 to 25, negative 0.5 meters per second squared. And from 25 to 30, negative 1 meter per second squared. All right. Assuming the object starts at the origin, so at 0 meters, draw the position time graph for the above scenario. So this is where, unfortunately, since I don't have a dot cam, I can't go through this with y'all in real time. So you might have to pause this several times to figure it out. But here's what I did. I took all these displacements. So it started at 0, 0. Then along A, it moved backwards 37.5 meters. So at 5 seconds, it would have a position of negative 37.5. Then along B, it moved backwards 5 meters. So at 7 seconds, it would have a position of negative 42.5. Then along C, it moved forward 5 meters. So it would have at 9 seconds, after moving forward 5 meters, it would be at negative 37.5. Along D, it moves forward 30 meters. So after 15 seconds, it would be at negative 7.5, having moved 30 meters forward. Along E, it moves forward while slowing down, still moving forward 30 or 25 meters. So that means after 25 seconds, it's at 17.5 meters. And then from 25 to 30 seconds, it moves backwards 12.5 meters. So that would mean that after 30 seconds, having moved back 12.5 meters, it would be at a position of 5 meters. So I scaled this out, and the first thing I did was plot my points from that. 0, 0, 5, 37.5, set or negative 37.5, 7, negative 42.5, 9, negative 37.5, 15, negative 7.5, 25, 17.5, and 35. And then I figured out how I would connect them. When the velocity is constant, so along from 9 to 15 seconds, that should be linear. So I connected these 2 points with a straight line. And then along A, B, and C, the acceleration is positive. We got a positive slope here. So the curve that I connect those with needs to be concave up. So something like that. And then from 15 to 30 seconds, the acceleration is negative. So the curves I connect those with need to be concave down. And that's how I sketch that graph. All right. Again, it's unfortunate that I'm not here to go directly over this with y'all, but hopefully I'll be back in school Wednesday, and then y'all can ask questions or whatever. If you come in for tutorials before school or during den, or after school on Wednesdays. All right. Describe how you can tell an object is moving forward or backward given a position time graph. Well, if it's moving forward, the slope of the position time graph is positive. And if it's moving backwards, the slope of the position time graph is negative. And for a velocity time graph, if the object is moving forward, the value of velocity is positive, so above the axis. And if it's moving backwards, the value of velocity is negative, so below the axis. How can you tell whether it's speeding up or slowing down from only a position time graph? We saw during the lab, if something's speeding up, the slope of the position time graph is getting steeper. And if it's slowing down, the slope of the position time graph is getting flatter. For velocity time graph, if the value is getting further from zero, then it's speeding up. And if the value is getting closer to zero, then it's slowing down. And if you have both the velocity and acceleration graphs, something speeding up when velocity and acceleration have the same sign, and something slowing down when velocity and acceleration have opposite signs. All right. I'll leave you all to do that, but you can check your work on it. And then finally, the last page. So when an object is traveling at a constant velocity, the position time graph is linear, the velocity time graph is constant, and the acceleration is zero. And then when an object's moving with constant acceleration, the position time graph is parabolic. Do not say exponential. It's not exponential. The velocity time graph is linear, and the acceleration time graph is constant. All right, so that's the notes for today. So again, this video and the notes will be posted. Hopefully I'll be in school on Wednesday, so that if y'all have any questions over this, you can do that. And on Thursday, we're gonna do these graphs right here. And don't forget, you also have homework that's due tonight or Tuesday night on AP Classroom. I'll also assign a new homework over like velocity or acceleration graphs and quantitative graphing. And then on Thursday, we'll learn the constant acceleration equations and start solving word problems. All right, so that's it, and y'all have a good day.